Thank you, Achintya, for doing this. Okay, firstly, I think what I'd like to ask is, how did you end up at CERN?
Ooh, very non-direct route to get to CERN. I studied physics back in India when I was at St Xavier's in Mumbai. From there, I came to London to do a master's in science journalism. And at the end of our master's, which was in 2010, the Large Hadron Collider had just switched on that March in 2010 after a 1.5 year break after they first switched it on. So a few of us from our course, because we were studying science journalism, we decided to pay a visit to CERN.
Right.
Got in touch with the head of communications and said we're a group of students studying science journalism. We'd be interested in coming and seeing the place and talking to you. I went along on that trip. Went to Switzerland for a day. Literally, we landed in the morning, flew back at night, and it just so happened that one of the experimental research teams there was looking for a science communicator, and I ended up joining a few weeks later. At the moment, I'm working for the Alan Turing Institute in London as a community manager. But I spent spent 10.5 years working at CERN as a science communicator.
Right.
First for the compact muon solenoid experiment, and then I joined the CERN central communications team for the last 3 years that I was there.
Was it something very particular about physics that made you write about like physics stuff, or you could have gone for mathematics or something else? Why physics?
I was interested in physics since I was about 6 years old.
Right.
And in particular, I think fundamental physics was very attractive to me, even as a teenager.
Mm-hmm.
I remember reading about CERN before it was, very much in the popular narrative. I remember reading the news about it when I was a teenager, and it's a place of research that was very inspiring, the kind of work that is done. So I was almost naturally drawn to the place.
Yeah. Right. And okay, so since we've just briefed a little bit about your history with physics, when you went to CERN and when you saw all of these researchers, scientists working on arguably the pinnacle of what it is in particle physics over there, what was it like on a day-to-day basis?
It was a great joy to be there as someone who's been in love with physics since I was very young, and who is almost like a fan of particle physics. To be in the midst of the research being done and to almost have my face at the window watching what's going on in the lab was a great joy and a great privilege. I think what's worth appreciating about how research is done is that at CERN you have the Large Hadron Collider, which is the biggest scientific instrument that has ever been built, which is this 27-kilometer underground ring, which is the world's largest particle accelerator.
Mm-hmm.
And there are different teams that analyze the collisions that are produced by this particle accelerator. And each of those teams is independently run. They're run by collaborations of universities, research institutes, national laboratories from all around the world, from over 100 nations, to come together to do this research. So you have a team that is operating the accelerator, that is making sure that the beams go from the proton beams from the time they're extracted from a hydrogen bottle, and they make their way through the chain of accelerators, enter the Large Hadron Collider, and then deliver the collisions to the experimental teams. And then you have the 4 major LHC experiments, which are, as I said, operated by independent research collaborations that then are responsible for collecting the data. When the collisions are taking place, you have people on shift who are monitoring the equipment, monitoring the experimental underground detectors, to make sure that all of the parts of the detector are working okay, and there's a lot of safety precautions that have to be taken. So there's this sort of shift work that happens on site, and when the accelerator is operating, that's a 24/7 role. So there are 3 shifts of 8 hours each, and there are people who are sat there monitoring the machine, making sure that it's running smoothly and so forth. At the same time, the accelerator team has their own shift cycle, and that's proceeding as well. And the rest of the researchers, because these are collaborations made up of a few thousands of people,
Mm-hmm.
They spend that time sort of analyzing the data. So you have the people who work on the data analysis side. There are people who are designing the next generation of upgrades to be made to the equipment, because as our technology improves, we're able to do the research better. So there are people investigating that all the time. There's sort of plans for maintenance that have to be done in the future. So it's very much like being on a ship, and you have to kind of control various things at various times. Not everyone is steering the ship. Some of them are charting the waters, and some people are there steering very much in real time. Some people are handling the sails and so forth. So there's a lot that's going on. You need big teams behind the scenes to be able to do this research. I think if you ask any of my friends from CERN about what their day-to-day life is like, they will probably tell you that most of it is meetings.
Right.
So most of your week is spent in different kinds of meetings. There are operation meetings, there are analysis meetings, there are meetings discussing latest statistical techniques that you're applying. There are meetings that are designed for discussing a research paper that is being advanced through various stages of internal review. And so you present the research paper and you sort of want to get your teammates, your collaboration to give you feedback. So there's different kinds of meetings that take place. There's long-term planning, 3, 5, 10 years into the future. There's immediate planning for the week's schedule and so forth. So there's a lot of meetings, there's a lot of planning, there's a lot of this stuff that happens behind the scenes.
Could you describe your work at CERN, like whatever you did when you were at CERN? You were there for nearly a decade, right?
Yeah, 10 and a half years.
Yeah. So if you could just give a bit of a piece as to what you did at CERN.
Sure. So when I was at CERN, I worked as a science communicator. So I didn't do the research obviously there, but I was there to tell the stories of the research that was being done. The storytelling involved either telling the stories in written forms. I would write articles about the physics, the engineering technologies behind the experimental setups, stories about upgrading the machine, stories about the people, the collaborations. You know, when you have over 100 nationalities represented there, there's a lot of rich cultural stories to tell as well. So there was different kinds of storytelling. Some of my work involved going down to the experimental areas, going to the accelerators, interviewing people about changes that were being made to the equipment, upgrades that were being done, planned sort of maintenance jobs and what happens after that. Talking to physicists working on latest analyses, writing news stories about latest papers that were published, but also background stories to explain certain concepts of physics as well. Another element of this communication and storytelling was taking people on tours of the experimental site, taking them around CERN and showing them, taking them 100 meters underground was a great joy, and then you know, take 20 people and show them a piece of equipment that's deep underground, which is a great experience as well. So that was another form of storytelling, telling them about the history of the experimental facilities, telling them about the history of CERN, about how the LHC was constructed and operated and so forth. So every day was a little bit different when I was there. I also started doing a PhD when I was there, and my PhD was in science communication, and I was studying the physicists and their attitudes towards communicating their research with audiences beyond their immediate peer group.
Right.
So there was also a bit of research to do for my PhD there as well. But day-to-day work was different, work was varied. Work gave me the opportunity to see some places that some of the scientists could not see, because if you work on your particular research project, there's very little reason for you to go into another experimental area, another part of the laboratory, because it doesn't concern your work. But for me, because I had to tell these stories, I had the privilege of going to see all of the accelerator campus underground. I went and saw many of the old accelerators that are still operational. It was a great joy to go and see, you know, some of the most complex scientific equipment that has ever been assembled. To be one of the few people to, you know, few among the thousands of people who get to see them. It was quite cool. It was a great experience.
And I mean, one of the reasons that I contacted you and was like very sort of excited in a way to talk to you was because I've been doing research for like a few years now. First, like I wouldn't really count master's thesis as a research, but like just that knack of diving deep into things and sort of like that. And now with my couple of years of my PhD, I could clearly see the difference between doing the research and being able to talk about your research. And with this YouTube channel, that's what I've been trying to focus more on. I should like bring more information so that it piques interest amongst people, so that because you never know who the next Einstein is, and you never know which piece of work is gonna excite that person to pursue this thing. So I think science communication is like one of the very underrated jobs, at least in my humble opinion. And it just feels like with people like you and with like mediums like YouTube and internet articles and all of things like that, it becomes a lot more accessible for a lot more people. And that's why this conversation is very important for me, because I had a very brief conversation with somebody who was working at CERN, and he was also at University of Helsinki, and we just by chance met at a lunch at my university campus. We worked from the same university, and she was there for a visit or something, and I had emailed her, and she approached me that I remember you from there, and we had like a 15-minute conversation as to what she was doing. And the fact that I could barely understand like 3 minutes of what she was talking about was something that I knew that this would be a very difficult thing to present in the form of a YouTube video. So having you is a very big opportunity for me, because you can, I've read your articles and I feel that you can dial it down to a way that people who have not really studied physics can be very much interested in what we're going to talk about, which is basically why we must learn that physics as we know it is currently very incomplete, and there are a lot of mysteries and a lot of things that we still need to be pursued upon and are worth pursuing upon. So thank you for coming, like the formal thank you that I had to do, to be fair.
Pleasure. Just if I can address that point, I think it's almost natural for one of two things to happen when you're doing research into something,
Right.
which is that you tend to have conversations with your peers most of the time about your research, and so you develop a vocabulary, you develop shorthand, you develop ways of, that are codified in research papers, that are codified in your grant proposals, etc. So when you speak to someone and you have a particular vocabulary in mind, then that stays with you and it becomes easier for you to grasp and easier for you to reach. Yeah. So it's a natural tendency for a lot of people to start speaking. Even when I talk about my research, you can slip into this mode of using terms that are very familiar to you and your peers, but might not be familiar to people outside of your immediate circle, and you don't necessarily know that that's the case. And the second thing that happens, I think, which happens with anyone who's done research, which you probably also understand, is that when you get very excited about the minutiae of what you're doing, you tend to dive right into it, and you want to focus on like the little, which can sometimes just be a great piece of insight into how people are fascinated by their work, and sometimes can be very difficult for you as an outsider to know what they're talking about. But
that's very true.
But yeah, that's fairly common. I think what's really nice is that a lot of people who work in research these days are more and more attuned to talking to people outside of their their immediate peer circle.
Yes.
And this is something that people are placing more and more importance into. So in an ideal world, you won't need a role like mine, because everyone's able to sort of switch between talking to someone who works in their field and someone who doesn't. But yeah, I'm quite happy to be here and speak with you.
Right, thank you. Right, so I think we should start with the first question. So this video is mostly about the standard model. How is it so incredibly successful? But for the physics to progress forward, there's a constant push for it to not be so successful and to find an anomaly of sort in a way. But first we need to address, why is the standard model so successful?
So the standard model of particle physics is a theory, a theoretical framework that has been assembled over decades. You could almost say it started to get pieced together in the 60s and has over the years expanded to what we call today the standard model of particle physics. This is a theory that encapsulates all of the known particles in the universe and 3 of the 4 known forces. So everything in the universe, all material substance, is made of matter, whether you drill down to the atoms, which are made of protons and neutrons and electrons, but then the protons and neutrons themselves are made up of particles called quarks, and then particles like the electron have heavier cousins like the muon and the tau particle. So the universe has a whole set of particles that everything is made up of, although only a few of them are stable enough for us to give stable matter, like you and me and stars and galaxies and so forth. So the standard model came to be assembled when people began discovering more and more particles, and they began realizing that some of the forces are related to one another. So you have the electromagnetic force, which is something that was unified between electricity and magnetism back in the 19th century. And that's a force that most of us are familiar with, whether it's magnets or light bulbs. We know what the electromagnetic force is and the interplay between them. And then there's something known as the weak force, which is responsible for beta decay and the reason that the sun shines. And you have something called the strong force, which holds those quarks together inside particles like the proton and the neutron. So the standard model has been very successful in describing in one set of equations all of the interplay between these particles and the forces, and also some of the force carrier particles that mediate the forces. Right. So you have the photon, which is a particle that many of your viewers might be familiar with, which mediates the electromagnetic force. It sort of interacts between particles that interact with the electromagnetic field. and you have the W boson and the Z boson, which is responsible for the weak force, and you have gluons, the intermediary particles associated with the strong force. The gluons glue together the quarks in composite particles. So this standard model has been assembled over decades and has been very successful. It explains everything that we know in the universe with one exception, which is gravity. And that's been a missing piece in our understanding of the universe. The reason we say that the standard model is very successful is that not only has it provided us with this explanation of the particles, how they interact with each other and the forces that are responsible for those interactions, it has also made predictions as a mathematical framework, behind the physical world. It can make predictions about how particles will be produced, how particles will transform once they're produced, and so forth. And so it has been making predictions for the last several decades, and the predictions have always been right. They've always been spot on. What's very interesting is that the standard model predicted things like the W and the Z boson much before it was actually discovered, a couple of decades before it was discovered, and then we found it and it was sort of exactly as it was predicted. And I mentioned these quarks, which are particles that the protons and the neutrons are made of. These quarks were discovered, they were predicted in the 60s. I think they were predicted in the 60s, and they've since been discovered. We found the up and down quark, which are the quarks that make up protons and neutrons. Then there are some heavier quarks related to it, like the top and bottom quark, and the charm and the strange quark. And the top quark was the heaviest, the last quark to be discovered. It wasn't discovered until the 90s. It was predicted to exist because people found the bottom quark. They said this must have an analog. And so the standard model has been very good at making these predictions, making predictions about the rate at which, when you collide two particles together, something else will be produced. It can give you a statistical model of how often certain physical phenomena will occur. So that's one of the reasons it's been considered very successful, and it's almost a little too successful, but we can talk about that.
Like, how are the experiments conducted in order to verify the standard model and its predictions?
So there are a wide variety of experiments that are performed at CERN, but I guess it might be worth focusing on the Large Hadron Collider, which is the flagship accelerator. And what you do with this big 27-kilometer circumference machine, which is located about 100 meters underground in the Geneva region in Switzerland, is you accelerate protons. You accelerate them in clockwise and counterclockwise directions. You accelerate them to very, very high velocities, so that the energy that is imparted to the particles as a consequence of the velocities to which they are accelerated can be transformed into matter when you smash those protons together. So at 4 different locations around this ring, you smash protons together at a very high rate. You have these collisions take place up to 40 million times every second in each of those 4 rings. So these collisions take place, they produce new matter, and then you have detectors around them that are very much like the camera that you have. They register particles hitting a sensor in some form. So your cameras are registering photons that are bouncing off of you and me. You have sensors inside these detectors that detect photons, that detect electrons, that detect composite particles like neutrons. You have detectors that detect particles called muons, which are heavier cousins of the electron. And by observing trillions of these collisions, millions of billions of these collisions, you eventually can paint a statistical picture of how the universe behaves. So by colliding 2 protons, you produce some particles, but you can't make any conclusions about them because you don't know whether that is within your statistical error range or so forth. So you need to produce lots of these collisions. And then you study phenomena that were predicted by the standard model. So when you collide 2 particles together, the standard model says, okay, you will produce an epsilon particle at this rate. You will produce a J psi particle at this rate. You will produce a Higgs boson at this rate. Every so many collisions, you will produce this. So then you record those collisions, and then you see whether whether the standard model has made the prediction correctly or not. So that's one way of studying the standard model. What was quite interesting when the Large Hadron Collider was switched on was that within 6 months, you had found all of the particles that had been found over the course of 60 years previously. So you switched on the machine, within 6 months you were able to collect the data to find all of the low mass particles very quickly. So that's one way of looking at the standard model, is to say the standard model predicts these particles will be produced. Can we observe them? You can observe them, then you know that the standard model is sort of doing its job. Another way of studying the standard model is by looking at the predictions that this theoretical framework makes
Right.
about some extremely rare phenomena.
Mhm.
So there's a kind of particle which is called a meson, which is made of a quark and an antiquark, and depending on which quark and antiquark that is made up of, they get different names. So there's one that is called the BS meson, and the standard model says that for every, if I'm not mistaken, billion times, 10 to the power 9 times that this particle is produced at the LHC, 3 times it will decay into 2 muons. Other times it will decay into other particles, but it says 3 in every billion will be pairs of muons. So not only do you have to produce the BS meson, identify that you have produced the BS meson, you have to then detect the number of times it is decayed into muons, and then figure out whether that fits your statistical prediction or not.
Right.
So any deviation from that, any time that if it is more than 3 times every billion or less than 3 times every billion, then the standard model is broken because the prediction was wrong.
Right.
So that's one way of studying whether the standard model
Works.
is correct, is accurate, that the predictions of the standard model are right or not.
Right. Why do you think that the standard model is too successful?
The standard model of particle physics has been a very good description of 3 of the known forces and all of the known particles. But there are some reasons why scientists believe that it is not a complete picture of the universe.
Mhm.
The most obvious reason being that the standard model doesn't tell you anything about gravity, which sits outside of the standard model of particle physics. So scientists are looking for a way to unify the standard model with gravity, different ways of doing this. If they were to be unified, we might expect that a particle associated with gravity might be found. So the other forces have a force carrier, like the electromagnetic field has the photon as a force carrier and so forth. That gravity might have a force carrier called the graviton, and if we were to find this particle, then that would say, all right, there is a means of unifying the standard model of particle physics with gravity. But there are also other sort of theoretical issues, other concerns about how the standard model makes certain predictions. And while we haven't found anything to deviate from the standard model's very accurate predictions, we do know that physicists have to artificially add some kind of corrections for things like the mass of the Higgs boson and so forth. While those corrections are perfectly valid things to do, the scientists they want a more pure explanation of why those corrections exist in the first place. And if you were to find another family of particles, which has been called a supersymmetric family of particles, they would naturally cancel out these corrections that have to be artificially made, and the Higgs boson's mass is what the standard model predicts it to be. So there are some gaps that scientists have known for a while that the standard model cannot make a very good prediction of, even though the predictions that it does make are spot on. What you then want to do is look for where there is a deviation from the prediction. So if the standard model says this particle will be produced X number of times every time you collide protons together, and then it will transform into something else Y number of times, and if those numbers don't align with what the predictions are, you have a door that somehow is open and says, right, we need to study this phenomenon more carefully, because that then potentially tells us where those deviations from the standard model will lead. What new theories can we apply? What new models can we apply on top of it to address those deficiencies? So the standard model is a very good, very robust theory, but it is by no means complete.
One of the things that really, as a layman, somebody just an enthusiast in this, I never really understand is how is something like dark energy or dark matter, which accounts for 95% of the universe combined together, how is that nowhere seen in the standard model predictions that it makes?
So the standard model doesn't tell you anything about dark matter or dark energy, but dark energy is a phenomenon that you can't really study at the LHC. So that's sort of ruled out from any of these explorations, because as far as we know, there is no particle associated with dark energy, so you can't find it by just colliding particles together. Dark matter happens to be something different, and although the expectations of us finding a dark matter candidate have gone down over time because it hasn't been found, people are still looking for it, because the role of a physicist is to look for whatever nature has to show. If it shows you something that you expect, great. If it doesn't show you what you expected, that's life. The way in which dark matter fits into the searches that are being done at the LHC for new physics phenomena is that I mentioned to you a few minutes ago that there is an extension of the standard model called supersymmetry, which predicts a doubling of the number of known particles in the universe. Now, doubling particles based on theory is not a new idea. Back when Dirac, who studied in Bristol, coincidentally where we are right now, when Dirac predicted the existence of something that he saw as the antiparticle of an electron, we hadn't seen any antiparticles, and it was only a decade or so after, or a few years after he made the prediction, 4 years after he made the prediction that we found this particle. And immediately you had twice as many particles in the universe as you had ever observed before or ever thought that might exist. So it's not unusual for mathematical equations to tell you that there's something that you haven't seen. The only problem being that we haven't seen anything that supersymmetry has predicted. So supersymmetry is an idea that is a theoretical model that says that for every known particle of matter, which is a fermion, there's a complementary force carrier. And for every force carrier that we know of, which is called a boson, there is a complementary matter particle. So these are called supersymmetric bosons and supersymmetric fermions, or bosinos and sfermions. Scientists have been looking at the Large Hadron Collider and elsewhere for the presence of these supersymmetric particles. And this connects with dark matter because the lightest supersymmetric particle is predicted to be stable, because light particles tend to be stable. And this might potentially be the dark matter particle that we're looking for, by being a stable particle that does not fit within the standard model.
Right.
That was one of the early ideas that were being explored. We haven't seen any supersymmetric particles, never mind the lightest one, we haven't seen any of them. So that idea is now being questioned to some degree. But I think what's important to remember is that we have only just scratched the surface of the data that the LHC is providing for analysis. We have just begun to scratch the surface. I think the LHC has so far in 10 years of running only about delivered 5% of its data potential. So there's still 95% of the LHC's data yet to be explored. And another thing to note is that although some of these particles have been ruled out, they have been ruled out by the simplest interpretations of the theories. So scientists usually start off by saying, okay, we'll just set a baseline and we'll look for things with the minimal set of requirements, but nature does not have to adhere to those minimal set of requirements. It could be a little more complex a story. So the same data are now being re-examined with some of the more complex interpretations as well, to see whether these particles still exist out there or not. So that's one way of looking for dark matter at the LHC, as far as I know.
I think you mentioned this before the interview off camera, but is there any significant research going on about quantifying gravity? Not just probably not at CERN, but anywhere across that you're aware of?
I'm not very aware of work that is being done in the various kinds of quantum gravity theories that are being done. A lot of them tend to be at very sort of advanced theoretical stages, but I don't know about what experimental setup has been made to look for those phenomena, because a theory is only as good as its ability to describe phenomena and predict phenomena. So a lot of theories are able to describe known phenomena fairly well, or extensions of existing theories can describe known phenomena fairly well. The proof is in the pudding, as they say. So you have to make a prediction that we can then test experimentally. That's when you say, right, this theory is pointing us in the right direction. But I can't really tell you much about work that is being done to quantify gravity.
Isn't that like the essence of experimental physics, or like physics in general? Theorizing it, and then experiments which are satisfying the theories that they make, and that's how we progress and figure out new stuff.
Yeah, so experiments, I mean, what's very interesting has been the interplay between theory and experiment. So CERN also has a theoretical physics division, where the theoretical physicists who come together and explore these ideas together, collaborating with one another. The role of the experimentalist is to simply look. The accelerator provides the collisions, the experimentalists then go through the data. What you base your choices for how you analyze the data depends a bit on the theoretical predictions. So what happens with something like the Large Hadron Collider is, I mentioned to you earlier that collisions take place 40 million times every second. Every 25 nanoseconds there are collisions taking place. There are about 1 billion interactions taking place at any given point, because 40 million, there's about 25 simultaneous proton-proton interactions taking place those 40 million times, so that's about 1 billion order of magnitude. So you have 1 billion proton-proton interactions every second, and you can't analyze them all, because every one of those snapshots that take place 40 million times a second is like a photograph. Each of them is about a megabyte in storage space. So every second you're producing 40 million megabytes. There's no way to store them, there's no way to process them, there's no way to analyze them. So you have to make intelligent decisions about what data to store and what to discard. And the discarding happens in almost real time, and it happens irrevocably. So once you throw away the data, that's it, they're gone.
It's gone.
You can't retrieve it. So from those 40 million, there are different kind of selections that are applied at the hardware level, at the software level, that reduce that data volume to about 1,000 from 40 million per second. Now, how do you decide what 1,000 to choose, right? And you program your equipment and your software to make those selections based on our current understanding of nature, which is the theories that are there and the phenomena that have been observed. But you also do kind of a random sampling, and every X number of collisions, you store whatever you see, because you never know what nature has to show. Nature doesn't have to adhere to our expectations of nature and our theory. Coming back to your question about quantum gravity, or quantization of gravity, I guess if there were a particle associated with gravity, then that's what we're looking for and hoping to find. Haven't seen anything remotely like it. And if we were to find such a particle, that might, again, point us in the direction of which of the many theories that are trying to unify gravity with other forces are maybe taking us in the right direction.
The major contradiction that we have in physics, not really contradiction, but like it lives in two realms. There's a realm of particle physics and there's a realm where we're existing right now. And we have two very different successful theories in there. In particle physics, we have the standard model, and then in a regular world, like in layman terms, we have the relativity theory. These are very highly successful theories, and they're not talking to each other in a way. Do you think that a unified theory, which somehow, like you said, bridges the two together with the help of gravity, do you think that that is an actual a possibility? Because for the past few decades, physicists have been doing it on and off, trying to make this unified theory, and some with more success and some with less. The Higgs was a great landmark in particle physics, and the gravitational wave similarly over there. But we still haven't been able to figure out how to bridge these two together. Do you think the unified theory, in your opinion, is something that exists?
That's a difficult question for me to answer. So I, having never studied these to that great a degree, I don't have an informed opinion, but I have maybe like a wish or a desire that we get there. So maybe my view on it is it would be really nice to have it. It was something that some of the best minds of the last couple of centuries have devoted their lives to. It would be very mean to personify nature. If we were to personify nature, it would be very mean to provide us with a whole set of things that can be unified and then leave some out, just tempting us to chase something that does not exist. So I don't know, it feels like it's a natural direction for research to take, and that we might be able to have a unified theory. What that would take from an experimental perspective, what that would take from new ideas of theories to emerge, I can't say, and who knows how long it might take. But I don't have an informed opinion, but I have like a desire that I hope that that's the case.
That's exactly what I wanted to know, because at the end of the day, I think science is something, at least for me, which makes me want to, like this knack of learning more stuff is something that stems from my interest towards science and interest towards physics and maths in general. And so we somehow, as humans, I think we tend to quantify these very technical stuff into emotional, not really emotional, but like contextual, humanized things. Like, so I'm very happy to know that somebody who's been at CERN for 10 years, in very close vicinity of all these people who are working at cutting edge of particle physics, which is like a mile away from what relativity is and all that stuff, but still has the hope of someday we'll be able to bridge those two together. That hope is very important for me, to be fair.
It would be nice. It would be very nice, because I think something that's quite valuable for us as people is to explore these questions in nature, these open-ended questions, exploring for the sake of exploring. And quite often we do this for satisfying our own curiosities, for answering questions about the fundamental nature of the universe. This is something that has fascinated humankind since our very early days, looking up at the stars and trying to figure out what exactly are they and what is our place in the universe. And these questions, they tend to be sort of philosophical ones. They seem to be very distant from our everyday life, that they don't really connect to anything that we do. But it seems almost inevitable that our advances in knowledge are in some way providing us with more tangible real world benefits. Mm-hmm. This is not to say that science just marches society onwards in the direction of progress, because we know that that's not the case. But a lot of the research that has been done into fundamental physics has given us some kind of practical outcome, which is, the hope is that someday the things that we're finding out now about the universe will continue to do that, and maybe a unified theory will help in that as well. And if you look back, understanding the relationship between electricity and magnetism helped give us electricity, really, and generators. These are benefits. Again, how we use them is up to us, but these are benefits that have emerged from humanity trying to understand the world around us, whether it's the world from the very distant past or it's the world that we can see right in front of our eyes. So, my hope possibly stems from that belief that someday the things that we discover, the knowledge will end up being beneficial to us.
Right.
And I hope that we use it in a way that is beneficial as well.
Right. I'm just stemming off from where you left off, like the philosophical part of science. How important is to actually fail in science? How important is that for the progress of science?
That's a question that a lot of people have spent a lot of time thinking about. As I understand it, when you do experimental physics, you're not looking to, going back to Kuhn's ideas, you're not looking to prove a theory, you're trying to refute a theory, you're trying to find evidence against what you're looking for. And that can open up very important directions for our understanding of the universe by saying this is what something is telling us and we don't find it. Just like we're looking for ways in which the standard model is wrong in the hopes that it'll point us in the right direction. Going back, almost 200 years ago, the Michelson-Morley experiment trying to find luminiferous ether in space was an idea that was very much in vogue, very much believed by the smartest people at the time. We didn't find it, and that null result was extremely valuable for then laying the path for special relativity and general relativity to come. Historically, finding null results is very valuable. Null results tells you what doors are worth closing and where other ones might open up for you. And in the early days, there was a very strong belief that at the LHC that finding the Higgs boson might be the worst thing to happen from this perspective. So you almost think we don't want to find it because then we have a null result and it's almost pushing us back to the drawing board to come up with some other ideas. Because if we find it, then you're again finding more evidence that the standard model is making predictions that are spot on. We wanted to make some predictions that are way off, so we then know where to go. So advances in science happen by finding things that we expect to find and by then finding things that catch us by surprise. Whether it is not finding what we expect or finding something that you didn't expect.
Where do you think physics is headed from here?
It's very hard to say. In many ways, the story of physics is a very long-term story. It isn't something that gives you immediate rewards. It isn't something that you find today will immediately tell you something about the direction that your research should go. We build up evidence over time. We use that evidence to then generate some ideas. And we use those ideas to perform some explorations. And the rewards can come some ways down the line. And as an example, the Higgs boson was predicted to exist in 1964 and then found 48 years later in 2012. It's one of the biggest gaps that we've had between predicting something and finding it. Although, to be fair, gravitational waves took even longer. They took a century from prediction to be actually observed. So where does physics go is very much an open question. It's a question that obviously carries a lot of political discourse around it as well. When you have research that is proving, when you look at it just in isolation, feels like a lot of money being spent on some experiments that are not giving us new knowledge, new immediate results. We spend $4 billion on building the Large Hadron Collider. We want something tangible tomorrow as soon as you switch it on. It's not how it works. But again, it is a very, it's not an obvious question as to what directions we should take in funding new research. Should we build a bigger accelerator? I think it would be very useful to build a bigger accelerator. But when you have a limited pool of money, you need to decide where that goes.
I think they are building a new accelerator, right? Which is
there are
100
plans.
kilometers or something like that.
There is a plan to build something called the Future Circular Collider at the moment, which personally I think is a rubbish name.
I was just thinking that in terms of physics, where they have put the most successful theory in particle physics as standard model, I think Future Hadron Collider is a very funky name for them.
Future Circular Collider. It's a circular collider and it will be built sometime in the future. But we don't know what happens when it will get built. We can no longer call it the Future Circular Collider. But at the moment, it remains an idea. It remains an idea that is being explored by people working on the technology needed to build it, needed to operate it, the magnets that we need for it, the vacuum technologies that are needed for it, the civil engineering work that needs to be done to put an accelerator of that size. It's also going to be an expensive endeavor.
Of course.
And society should then ask itself, is this worth funding? The feeling among member states of CERN is that it is worth funding. It is worth building something in the future. But people look at the money and they say, oh, this is a lot of money. And there is an argument to be made for exploring in new directions, at higher energies, with newer satellites, telescopes in space, with experiments that are sitting on the International Space Station, although what happens when the International Space Station is no longer in space remains to be seen. But I think these are questions that are worth us asking as a species and worth putting money into finding the answers.
Worth exploring, yes.
Worth exploring.
How was it? You were there when the Higgs boson was discovered, right? How was it at CERN when something as monumental as this, which is gonna define a generation of physics? How was it when you were there and this thing was happening?
It was great. It was
like just before you began, I was there on the 10th anniversary.
Yeah, you went like your trip coincided with that. Right?
Yeah, it coincided with that, and it was very nice in a way that I didn't get any sort of special treatment, which I don't know why I was expecting that, but it was very nice in a way that we got to see CERN and like some of the historical parts of it, and the tours were very it was very oriented towards Higgs boson.
So the announcement of the discovery of the Higgs boson was probably the highlight of my career, easily by a long shot. I joined CERN in 2010, and 2 years later we had found this particle, and the build up to it was a lot of fun. The build up to it was great because I was in this position where I could see everything that was happening in one of the teams. So 2 experimental teams found the Higgs boson, CMS, which I worked for, and the ATLAS team. And since I was in CMS, I sort of knew what was happening. I knew that CMS had seen something. But when you walked around the lab, you could see sort of like people smiling a little too much, and you knew something was up. But you had to wait until the 4th of July to know that ATLAS had also found the same thing. And that's quite important in particle physics, because you can't take the word of one experimental team. It's not about a question of taking their word. It's that you do not know whether a phenomenon that you observe is nature showing you something new, or is the consequence of an error in your equipment, an error in your calculations, an error in your computing, whatever it could be. So to have 2 independent teams that are using different equipment, different methodologies, doing the analysis separately, to then be able to come to the same conclusion, that really solidifies your belief that you have seen something new.
Of course.
So I knew what CMS had seen, and then I was waiting eagerly to see what ATLAS had seen, and it was a great day. It was just, there was so much joy all around. Everyone was just buzzing, people were just happy and also relieved, because a lot of people had, a lot of the physicists had worked very late hours in the lead up to the announcement. They had put in very hard hours, long days, weekends, just doing analysis, checking them, cross-checking them, producing new plots, going through the motions. It was a lot of work for them. And so not only was it an occasion for them to celebrate what they had done, it was also a sense of almost like letting go and just accepting that this was where we are, and taking like a day off to just enjoy the feeling. It was a great occasion.
When you were building up to discovery of the Higgs boson, you were working, I think, for a couple of years at that point of time, right? So did you feel that this is the next big thing that is going to happen in those 2 years of build up? And if that is the case, then what do you think is the next big thing that CERN is working on right now?
Well, so the thing is, when you have these protons that are colliding into each other in the machine, right? The same data sets can be used for looking for a variety of physics phenomena. So you have to this day multiple teams within the experimental collaborations that are all doing different analysis. They're looking for different things. So it isn't as if you devote your entire energy to do one thing and then you switch to doing something else. When you have a team of a couple of thousand people, 2,500 people working on the analysis, you have different teams, dozens, working on different research. So some of them are studying the standard model predictions. They're just exploring that. There are some that are looking for beyond the standard model physics. There are some that are studying the Higgs boson and its properties and so forth. There's different research that is being done in parallel. But at that time, in the 2 years leading up to it, it was particularly fantastic because the LHC was built with the objective of either finding the Higgs boson or ruling it out. And that was the idea that, very quickly we will do that. But of course, there's a lot of exploration still to be done, but it was felt that very early on you could do one of those two and then sort of decide how your future explorations are going to go. And so because it was expected that if the Higgs exists, it will be found with fairly small amount of data. It's a small amount, you're looking at 500 trillion proton-proton collisions. The early searches were of course devoted to this. A lot of the teams were focused on looking for the Higgs boson. There were teams who were doing other physics. And one of the reasons you have to do the other physics as well is you need to understand the background in your data. You can't just look for a signal without knowing the background. So when you have a new machine, a new energy regime, new collisions taking place, you need to know what the standard model phenomena are like. So there are people doing that and there are people doing Higgs physics. Yeah, it was very cool because people knew that they had to look for it and they would either find it or rule out the presence of the Higgs boson in a very large mass range. And then you have more interesting questions popping up. But it was found fairly quickly, and I think it was found earlier than expected because people began applying more innovative techniques to how they analyze the data. They began pushing themselves to the limit and the machine to the limit.
Right. Now that explains it pretty well, I think. Thank you again. This is like the final time. Thank you.
Pleasure.
Thanks, man. Cut. Chal, bhai, done.
Me, and then it's like all along.
Yeah, so first you ask the question and then you pass on the mic to him and then he'll answer and then you can pass it on. Okay? We go in this way.
Aye. Yeah. What's the most complicated maths equation you know?
Ooh, that's a good question. I haven't thought about maths equations in a long time, but one of the most complicated physics equations I know is on my shirt.
Oh, I see that.
Yeah, it's a particle physics equation. It describes. Yeah, he knows everything. He's already told us he knows everything. It's an equation that tells you in 4 lines about all of the forces in the universe and all of the well, not all. It doesn't tell you about gravity. You know the thing when you dropped your bag earlier. It doesn't tell you anything about gravity, but it tells you about everything else and all of the particles in the universe that matter is made of. So this is, I think, the most complicated equation that I know of. Don't ask me to explain it. I don't know how to explain it. I just know he's gonna. Yeah, go on.
So, yeah, that.
Yeah, he's gonna give an explanation off camera later on
Yeah,
in private.
yeah.
Yeah. Oh, some hot chocolate. Yeah.
Yeah.
Next question.
Alright. Have you ever read a story that was a man walking around and
Adam, no, it's about maths.
yeah, and a apple fell on his head and he picked it up.
Oh yeah, that's
and
the guy
he
that
threw it,
gravity.
and he threw it on the ground, but it didn't go with gravity. It didn't go up back into the tree.
Yeah.
So have you ever heard of a story like that,
Yeah,
or like
everyone
something different like that?
Obviously.
Yeah, the tree fell on his head.
The tree fell on his head. The whole tree. Oh, I'd have been dead if the tree fell on his head.
No, the apple.
The apple. So the story is that a famous physicist called Isaac Newton.
My name's Isaac.
Is it? Is your last name Newton?
Yeah.
Yeah.
Yeah, okay. Yeah, so apple fell, allegedly. We don't know, because it's a story, but we don't know if the apple really fell on his head or fell on the ground. But he was wondering why the apple fell, and he began thinking not just about why the apple falls, but why the moon revolves around the earth. And the fact that the moon revolves around the earth and the apple falls onto the earth are related, and that was his big insight. Next question from the expert in physics that we have over here. What's your name?
I know all about physics, so I'm just going to ask you a question.
Okay, yeah, that's fine.
Because I know all about
He's
physics.
testing me.
Are you better at physics or maths?
Oh, good question. Physics, probably, slightly, yeah. Slightly better at physics than maths, yeah. I studied both when I was in university, but I wasn't very good at maths. I was slightly less bad at physics. Final question.
Do you play football?
Badly.
Yeah. And everybody subscribe to Altinfinity, please. Yeah. Like and subscribe.
क्या हो रहा है?
मेरा question.
अच्छा.
Hello. ठीक? Okay. So it's a general question, and it's kind of general to all researchers. So me being in software, we are usually given deadlines for like quarters. Like we know exactly what our aim is going to be at the end of the quarter. As a researcher, in an institution like CERN, what are you like planning for? Like, are you just getting data and then planning for the next day, or like, how does it go? Like, how do you plan?
That's a good question. So research is still funded in cycles for certain durations. People, when they go and seek funds for their research, they're given X amount of money to deliver something by X amount of time. But when it comes to particle physics, what happens is a little interesting. The thing is, you could keep refining your results endlessly without publishing them if you wanted to. Okay. Because the more data you get, the better your results are. So you can just keep, just let it get a little bit better, a little bit better, a little bit better. So it almost seems as if particle physicists artificially give themselves deadlines, which is in the form of scheduled conferences in the year. Okay. So every X months, you have a meeting where you present whatever you've done, everything that you've done. And you usually set yourself a target saying, by this point, we want to have analyzed this quantity of data and present these X number of results. You want to present results in this area of physics, this area of physics, and this area of physics, these many results, and we want to have analyzed this amount of data. And you're almost driven by your scientific rivals who also have the same amount of data to play with, and they might present something that's slightly better than yours, and you don't want them to present something better than yours. So you sort of motivate each other. You motivate one another to drive yourself to presenting something. So there are sort of schedules. There are some conferences that take place every 2 years, which are like flagship major conferences, which everyone prepares for. There are other ones that take place every year. There are ones that are spread out throughout the year. Okay. Conferences are very important. Another driver of it is graduating students. So if you're a physics PhD student, you need to submit your thesis for you to graduate. You have a certain number of time to do that. So you start working towards presenting your results there. That's another motivator as well. So there are lots of different factors that result in people presenting physics results. They also present what are called performance papers, where they describe how well their machines are performing. Okay. And you want those out as early as possible because that can help inform the decisions about how you conduct the research in the future. So there are certain internal and external boundaries that you set, factors that you set that then lead you towards presenting your results.
Cool. And it seems like something it's more individual based. Like a professor is gonna set himself a target, but how is CERN as an institution setting boundaries on like how long a researcher is gonna work on one particular project? Or
that's again a good question. So what's quite interesting is the different ways in which the different granularities in which teams work. So you have these research collaborations. The two biggest ones are Atlas and CMS, and they have every research paper published by them has about 2,500 signatories. 2,500 people are co-authors on every one of these papers. But of course, all 2,500 are not doing all of the research. You have smaller groups of people doing the research. So you have groups that are in dozens. They're led by like collaboration between 3 or 4 universities with professors, PI, principal investigators, their postdocs, their doctoral students working towards this. And they kind of work together, and then the collaboration as a whole sets a plan that says we want to achieve this by this point. CERN as a whole does not really set conditions on how the experimental teams do the research. CERN is both a host for the research, where the scientists from around the world come to do their research, and CERN is the laboratory where they can do the research. And CERN is also a member of these research collaborations. So some scientists who are paid by CERN are part of these research teams as well. Okay. So they don't really dictate how the research is done, but a lot of this is just awareness of people saying, we know by this time we have the capacity to do this, so we're going to push ourselves and get that done.
All right, yep, that answers it. Cool.
Shall I switch this off?